In progress.
Hi, my name is Jashanpreet Singh Kamboj, and I am here to discuss the task 9.1C, 9.1P. It's a past grade task. Uh, let's go with the first question. Uh, when we I'm explaining the first question. When we use the depth first search algorithm on a graph, the running time depends on how we represent the graph. If we use an adjacency matrix, the graph is stored as 2D array where each cell at position I and j indicates if there is an edge between node I and j. When we move to checking for the edges with an adjacency matrix, checking if there an edge between two node is very quick. It take a constant time, which is O of 1. But to explore all the neighbors of the node, we need to go through an entire row or column of the matrix, which takes one time for each node. By wasting nodes for exploring the neighbors during DFS, we visit each node exactly once, which takes O of n times. Since there are n nodes, for each node, we look at their neighbors, uh, which takes one time per node. So if we multiply the time it takes to explore the neighbors for each node by the number of nodes, the total running time becomes uh, O of n square. In as we can see over here, uh, in contrast, if we use an adjacency list to represent the graph, DFC would take O of n plus 1, where n is the number of nodes and m is the number of edges. This is because we look at the actual number of each node. So with the adjacency matrix, the time complexity of TFS is O, O of n square, whereas the adjacency list, it is O of n plus 1. This is a now we move to second question. Uh, when we talk about the time complexity, Dijkstra's algorithm has a time complexity of O of v plus e log v, where v is the number of vertices and e is the number of edges. On the other hand, Flood's algorithm has a time complexity of O of V cube. As the number of vertices increases, flood algorithm becomes significant and slower compared to Dijkstra's algorithm. When we talk about the space complexity, Dijkstra complexity use a priority queue and some other data structure resulting in the space complexity of O of V plus E. In contrast, uh, Flood's algorithm uh, uses a matrix to store the shortest distance between all pair of vertices, leading to a space consequently of O of V square. When we talk about the problem size, if the graph is small, uh, the performance difference between the two algorithms might not be negotiable, and Floyd algorithm can be easier to implement. However, for large graphs, Dijkstra's algorithm is more efficient and scalable. When we talk about the negative edge weights, uh, Dijkstra algorithm only work with non-negative edge weights. If the graph contains negative edge weights, uh, Dijkstra algorithm is not suitable. Flood algorithm, however, can handle negative edge weights, making it easy, good option for graphs that include them. When we talk about multiple sort destination pairs, Flirt's algorithm computes the shortest path between all pair of vertices in a single run. In contrast with the Dijkstra algorithm, we need to run it separately for each source vertex if we want to find the shortest path between multiple pair of vertices. Given we have a colleague problem where where we need to find the shortest path from the user's location to multiply the tourist sites. Dijkstra algorithm is probably the best choice. It is efficient for graphs with non-negative distance and a moderate number of locations. However, if the graph has negative as weights, or if our colleague need to find the shortest path between all pair of vertices, Floyd algorithm might be a best choice despite being slower. Thank you for the discussion.